Today we're going to talk about equation intuition in electrochemistry. So first, there is this equation that relates the standard reduction potential, or the E cell, to Gibbs free energy. So if you have a voltaic cell, E cell is usually positive, it's spontaneous, so Gibbs should be negative. It's a good way to check your answers. Now, the fundamental principle of all voltaic cells is that the E cell of the cathode minus the E cell of the anode will give you the E cell of the entire net cell combined, which is your voltage here. So it's basically the voltage of cathode minus the voltage of the anode will give you the voltage of the net cell. And this can be done in standard conditions, and that would be easy. You would just find values from your formula sheet. Standard conditions include 1 molar, 25 Celsius. Okay, but when it's at non-standard conditions, instead of finding the voltage for each individual cell from the data table, you'll have to calculate. So you can calculate the E cell at non-standard conditions using this relationship that relates the non-standard E cell to the standard E cell, and that is this. So this is used for one cell, so that means it could be one cathode cell or one anode cell or one net cell. The only difference is you would modify this standard reduction potential and this Q. If you're doing it for one individual cell, like you're substituting this entire formula into here and here, if you're doing that, the Q will just be 1 over, that thing which is being reduced. Being reduced. But if you were going to use this equation for the entire cell, you would need to make sure that this E cell standard is from the data table, E of cathode minus E of anode, both as standard, and the log Q would be actually your product over reactance. So it depends. You can use this equation for an individual cell or a net cell. You just need to make sure that the values you put in here are correct. Now, if the situation is at equilibrium, which means there is basically no voltage running, so that means the E at non-standard would be 0, and canceling out for 0 here will give you this equation of E, the standard reduction potential is equal to 0.0592 minus number of moles of electrons transferred, okay, and log of K. So there are also questions that relate K to the E cell, and how do we go about that? So in the situation of K, if you're doing it for one individual cell, either the anode cell or the cathode cell, you would be putting the standard reduction potential into here. So for example, this would be the reduction at the cathode. But even if it were at the anode, when you put it in this equation, you would use a reduction half reaction. So you would still just write it out like this. So that means since it's product over reactance and solid's not a product, solid's not in our ICE table, it's not in the K expression, so it's only going to look like this, even for the anode. And now, let's say you don't know what concentration this is. So how this is related to K and the ICE table is because this concentration is a concentration at equilibrium. So you might have a reaction. It's usually a complex. It's either going to be a K of formation or a K of solubility. So you would write an ICE table depending on formation or solubility. And this concentration that you need to find or you need to connect is going to be like here. Okay, so then you need to find this in order to find some number for this. And to find this, you can use the KSP or the KF and just write out, the x's correctly with their powers. So then once you find the x, once you isolate for the x, you can put it back into your concentration in here.